Hello everyone and welcome to your third historical geology lecture. So we're still in this phase of just kind of getting you guys set up to understand the very basics and foundations of earth science so that we can move on with our more in depth our study of historical geology. So this is a lecture on earth structure, so basic earth structure, because basically what we're going to be doing is I want you to understand what the earth is made of and how it's set up and formed, and you're going to have to understand these things once we get more in depth into historical geology, which actually, just to kind of let you know, really the second half of the course is historical geology, and the first half is kind of just getting you ready and giving you the background you need to understand historical geology. So it's actually going to be a lot of earth science and physical geology, so kind of getting you acquainted with rocks and minerals and structures, geologic structures and formations and things like that. And then we're going to talk more in depth about, after the first midterm, we're going to start really getting into hard historical geology. Not difficult, I mean just the real historical geology. So anyway, just kind of let you know what's coming up here. So this is just a lecture on earth structure, so you know what the earth is made of. So some basic facts about the earth. It has a layered structure. So it's got four main compositional shells. So what is meant by compositional? Well, compositional means that these shells, you see four, 1, 2, 3, 4, are made of different things, right? They compose different things. So we're going to talk about those. The first is the crust. That's the outer shell. It's very thin. You can almost think of the crust as kind of like the peel of an apple. It's that thin. Okay, very, very small. It's only about 0.6% of the Earth's total mass. So it's pretty small. It is made of relatively less dense stony material. Okay, so the crust is made of stone, made of rock, and it's relatively less dense compared to a lower rocky layer called the mantle. The mantle is the big boy of Earth. It is 2/3 of Earth's mass. Okay, so 67% of the Earth is the mantle. And the mantle's rock. And a very important point here is that the mantle is solid rock. It is not a liquid. It's not magma. It's nothing like that. It's solid rock. So it's not only solid rock, but it's made of a different kind of rock than the crust. So the crust is kind of lighter and less dense. The mantle is denser kind of rock. The next layer below that is the outer core. And the outer core is liquid. It's the only shell of the four shells that is liquid. It is liquid iron nickel alloy. Okay, so it's about 95% iron and nickel. It's probably about 90% iron, 5% nickel, and 5% other stuff. Okay, things like silicon, sulfur, carbon, oxygen, things like that. The last final layer is an inner core, which is solid iron nickel alloy. Okay, so the core is about 1/3. The outer core, inner core together is the core, is about 1/3 of Earth's mass, and it's about half of Earth's radius. Okay, so if you were going to drill down directly into the center of the Earth, you would be going through the crust for a very short time, and then you would start to be going halfway through the mantle. So imagine you're living on here on the crust. Okay, there you are. You start drilling down about halfway down, you're going to hit the core mantle boundary. Sometimes that core mantle boundary is called the CMB, which means core mantle boundary. Okay. So the crust is solid rock. The mantle's solid rock. It is half of the Earth's radius. The other half is the core. However, don't be confused. It's half of the radius, but it's 2/3 of the mass. The mantle is, Okay, so it's half the Earth's radius. The other half is the core, but the core is only 1/3 of the Earth's of the Earth's mass. Okay. Outer core. So once you get to the core mantle boundary, you're going to start swimming in red hot 4,000 degree liquid iron. Okay, so you're going to go through that. That's the outer core, and then you'll hit solid iron nickel alloy. That's the inner core. Okay. So that's what your trip through the Earth would be like. Now take a look at how this is a diagram that not only shows kind of the compositional layers of the Earth, but also the temperature. So notice as this line here, this yellow line, moves to the right, it gets hotter. Okay, so it starts at 0 degrees Celsius, which right now in your room that you're watching this in, you're probably sitting here at about 25 degrees Celsius. So you'll notice this goes all the way in thousands, 1,000, 2,000, 3,000, 4,000, 5,000 degrees Celsius. Extremely hot. You know, think of white hot. So you could see kind of how they change the colors of this stuff. You know, a lot of the mantle. I mean, the mantle is so hot. I mean, it's 12. It's really most of it is probably around 1,200 degrees Celsius. So it'd be glowing, you know, bright orange red hot if you could actually get down in there. Okay, it's glowing bright orange red hot. If you got into the core and the inner core, it would be white hot. You know, white hot and molten steel, basically, is what's down there. So it's pretty amazing. You know, there's a lot of energy inside of it, and that energy has a hard time escaping. You know, because the Earth is so well insulated. So anyway, I want to take a look at this temperature. You notice the temperature increases very rapidly through the crust. Okay, so you go from 0 to about, you know, almost 1,200 degrees. Whoa, 1,200 degrees. Gosh, I'm not drawing a very straight line. Celsius, as you go through the crust, and then when you through the mantle, it's kind of the rate of temperature increase slows down a lot. You get to about 3,000 degrees Celsius when you get to the core mantle boundary, and you get to maybe 4,800 degrees Celsius as you get to the inner core. Okay. Just some basic stats about the Earth. The mass is 6 times 10 to the 24th power kgs. Okay, the radius is about 6,000. You can think of it as 6,400 kilometers. Okay, so you'd have to drill down 6,400 kilometers to get to the center of the Earth. That puts the core mantle boundary at about 2,900 kilometers. Okay, so you'd have to drill down 2,900 kilometers to get to the core. The density, this is a very important fact. I want you to know the density of Earth, about 5.5 grams per cubic centimeter. Okay, and that compares very well to the densities of the other terrestrial planets, you know, Mars, Venus, and Mercury. Now, the age of the Earth is about 4.6 billion years, 4.55 billion years old. That's when it accreted together. That's also when, by the way, the age at which the solar system, the moon, a lot of our solar system bodies accreted together. So the solar system formed very quickly. Just in, you know, tens of millions of years it formed, and we've been kind of just going around the sun ever since then, right? So for 4 billion years, 4.5 billion years. So the density I got there, top 4 elements. This is something you want to know. So these are the top 4 elements in the entire Earth. Okay, so top 4 are iron, is number 1. Oxygen, number 2, silicon, and magnesium. Okay. So it might interest you to know that the bulk Earth is similar in composition to something called chondrites. Chondrites, I guarantee probably most people haven't heard of this word chondrites before. Chondrites is a type of stony meteorite. So when we take a look at the meteorites that strike Earth, we notice that it is pretty close in composition to what we think the whole Earth is. Okay, so there's the same ratio of metal to stone, and the same ratio of like oxygen and magnesium and silicon and iron that we imagine the Earth has. And that's very simply because, you know, the Earth accreted together and came together from meteorites, little by little. Meteorites, large ones, not just these small guys that strike Earth, but large meteorites kind of conglomerated together and gave us the Earth. That happened very fast, just in tens of millions of years. So this is the breakdown of Earth's composition. Okay, it's very similar to that of a meteorite, a stony meteorite. It's iron, 35% iron, 30% oxygen, 15% silicon, 13% magnesium, and we have the fifth one, sorry, is actually nickel, which is in the core, sulfur, calcium, aluminum, and all the other stuff is less than 1%. So, a lot of you might think, like, what about carbon? Like think about all the carbon-based life forms on Earth. Well, that carbon is a very, very small, very, very small amount. There's actually a very tiny amount of carbon on Earth, but yet all of life is composed of that carbon, at least in part. Okay, so we're going to take a little stroll through the Earth and looking at each of these layers in more detail. So first layer is, as you know, the crust, right? So the crust is that outermost layer of Earth, and it's not very big, okay? It's only 1% of Earth's total mass. It's not even 1%. It's actually 0.6%. Now, over the continents, the average thickness of the crust is 30 kilometers, but it can be up to 70 kilometers in places where there are mountain chains like the Andes Mountains or the Himalayas. Over the oceans, the average thickness it's thinner, so the crust is only about 5 kilometers, maybe only up to 7 kilometers, okay? So you're going to see that we have two flavors of crust. We have ocean crust, and we have continental crust, okay? And they're very, very different from each other. They have things in common, but they're very different from each other also. So what is the crust made of? It's a little bit different than the bulk Earth, the whole Earth composition, okay? So remember, in the whole bulk Earth, we had 35% iron, 30% oxygen, and like 15% silicon, 13% magnesium. Now it's kind of a different story in the crust. The crust kind of sequesters, or it sucks in the lighter elements. So the first and most abundant element you'll notice, maybe to your surprise, is oxygen. So the crust, the actual rocks of the crust. So if you go outside and you pick up a rock, 50% of that rock's mass is probably just oxygen. So that might kind of surprise you, because you probably think of oxygen as a gas, and it is, of course, a gas, but it can also combine, like you guys maybe know that like rust, like the rust that forms on a bicycle or a car, is iron oxide, right? It's iron and oxygen combined together, and it can form a solid. So that's what happens actually with rocks. The oxygen has combined with the silicon and other elements, and it's formed a solid, okay? So the first one is actually oxygen. So you go outside, pick up a rock, it's probably 50% of that rock's mass is probably just oxygen. The next one is silicon, okay? Next one is aluminum. And iron, which was number 1 in the whole bulk Earth, is number 4 in the crust, followed by calcium, okay? You'll see there's other things here too, sodium and potassium. Magnesium is up there too. Hydrogen, like the hydrogen in water, for instance, is up there. And you see still carbon doesn't make the cut, which maybe might surprise you, because you would think all the life, it's all carbon-based life. You think it might be up in the top 5 or something, but it's not. Carbon is not even 1% of the Earth's crust. It's only, whatever. It's probably like 0.2% or something like that. Very, very small. So here's your periodic table, right? Here are the main, the big boys, okay? So oxygen, aluminum, silicon, iron, calcium. Here are kind of secondary important elements in the crust: hydrogen, sodium, potassium, and magnesium, okay? So you want to know all those. I kind of guarantee you I'm going to have questions on the midterm. I'm going to have questions on the final about what is the crust made of and what's the whole Earth made of in terms of bulk composition of the elements. Okay, so you got to know that stuff. It's absolutely required and important. You got to know coming out of this class what the Earth is made of. Okay, so moving right along to continental crust and oceanic crust. This is another topic I ask a lot of questions about on the test. I could almost guarantee you I'm going to have a question on the test about this. You need to know, both on the final and midterm, by the way, you need to know the difference between continental crust and oceanic crust. So oceanic crust is like basalt rock from the seafloor. this is, if you go to basically any place in the ocean and you drill down, this is what you're going to find is the basis of the crust there. It's basalt. Basalt and another rock, gabbro, but it's basalt, mostly basalt. It's a black, very plain looking igneous rock. And we're going to learn about igneous rocks a little bit later, probably next week or the week after. Okay, so the crust rocks beneath the oceans are very different than the crustal rocks of the continents. So if you go into the oceans, it's basalt. The density of the crust, it's very important. You need to know this. It's about 3.0 grams per cubic centimeter. Now, do you all remember the density of the whole Earth? It was 5.5 grams per cubic centimeter. Why is the whole Earth denser than the oceanic crust? The reason is that when you talk about the whole Earth, you're also talking about the core, which is solid metal. And you might know that iron is a pretty dense material. It's denser than a rock. Like if you could imagine yourself just like picking up a hunk of pure iron versus picking up a hunk of pure rock, you'll know the iron is going to weigh more, okay, because it's denser. So the whole bulk density of the Earth is denser than that of the crust, okay, because of that iron core. Now, things are different on the continents. I show you this pretty cool picture. This is from City of Rocks National Park in Idaho. It's a pretty cool granite outcrop of rocks. Now, continental crust is not made of basalt necessarily. The continents are much more what you could call heterogeneous. So it means that they're made of different things, right? Hetero is different. Genus means type, so different types. So heterogeneous, it has a heterogeneous composition. It's made of different types of rocks. Okay, there's a lot of basalt. There's a lot of granite. City of Rocks is made of granite, for instance. There's a lot of a rock called andesite. But if you were to take the whole continental crust and put it in a big blender and blend it all up, it would have the composition of this rock right here, which probably a lot of people have not heard of, called diorite. Diorite. Well, you need to know this rock from now on because it's a very important rock because that's the average composition of the continental crust. Okay, diorite. It's not granite. I remember one time I was listening to a pop song on the radio, and this pop music girl was like, "We're just floating on this big ball of granite." Really made me cringe because we're not on a big ball of granite. You know, Earth is like 1/3 metal, right? The mantle is not made of granite. So really, and not even the continental crust is made of granite. We're made out of something called diorite here on the continent. So granite is actually a relatively rare rock. So there's a lot of variation in rocks of the continents, but they have an average composition of diorite. Okay, so there's some more pictures of granite. Okay, granite is it is on the continents, but you won't find granite on the ocean floor. Okay, it's a continental rock. Now the density of continental crust is 2.7 grams per cubic centimeter, which you'll notice is lower than bulk Earth and lower than the density of the ocean floor rocks. That's extremely important. That small difference in density has huge implications for your life. You might be looking at it and thinking, well, what does it matter? 2.7 grams per cubic centimeter versus 3 grams per cubic centimeter. What does that matter? That's no small beans to me, but actually your whole life depends upon the fact that continental crust is less than has a less density than ocean crust, and I'll explain that a little bit more later. But you do need to know this at this point right now. Continental crust is less dense than ocean crust. Now, continental crustal rocks have more silicon, more oxygen, more aluminum, and more sodium than ocean crustal rocks, which are richer in iron and magnesium. We're going to learn more about these things as the class proceeds. Okay. So let's compare these two. We'll just put them right next to each other. So that's, if you were to take an average representative of the continental crust, it would look like this diorite. If you were to take an average representation of the ocean crust, it would look like this basalt. Okay, so you'll see that this is kind of like a salt and pepper rock. This is a black rock. And you're going to see why that has implications for later when we talk about igneous rocks. Okay, so remember the continental crust is thicker. It's about 30 kilometers thick, whereas ocean crust is on average only 5. Continental crust is less dense at a mere 2.7 grams per cubic centimeter versus the 3 grams per cubic centimeter of the ocean crust. There is more silicon, oxygen, sodium, and aluminum in the continental crust, and the ocean crust has more magnesium and iron. So this is what it would look like as a diagram. There's the continental crust and the ocean crust overlying the mantle. Okay. And by the way, the continental crust is actually, it's not all homogeneous like this. Remember, the continental crust is heterogeneous. That means composed of different types, whereas the oceanic crust is more homogeneous, one type, homogeneous, right? So the continental crust, by the way, is actually a little bit, I don't like this picture just because the continental crust is actually a little bit compositionally stratified, which means that as you move up in the continent, it actually becomes more and more different than the ocean crust. The continental crust that's down here is actually pretty similar to ocean crust. And it kind of fades in a gradient as you get to the top, and it becomes more continental than oceanic. Okay, so just wanted to let you know that. Now, I think I was explaining before, just a couple slides ago, that it's really important for your life that you have this density difference between ocean crust and continental crust. So why is that? Well, the reason is this. So the mantle is actually, even though it's solid, it's a soft solid that can actually move. It's pliable. You can almost think of it as silly putty. The denser, thinner ocean crust is sunk lower into the mantle because it's more dense. The thicker, less dense continental crust is sitting a little bit higher than the ocean crust because it's less dense. Okay, so this whole principle, by the way, is known as isostasy. It's just a kind of a gravitational equilibrium, you know, where less dense things are going to be more buoyant, quote unquote buoyant, and kind of sit a little bit higher than denser materials. Okay, so the reason this is important for you is that if we didn't have this lower density of the continental crust, the continents would just be sitting at a similar level as the ocean crust, and we'd have a lot less elevation, you know? So we would maybe be underwater if we didn't have, or there'd be a lot less crust exposed on the surface if our density was the same as the ocean crust. So there might not even be land above the water level. So it's actually a very important thing for you. And another thing is, if it wasn't for our lower density, continental crust would also get sucked back into the mantle during subduction, which it doesn't do that, right? Ocean crust gets sucked into the mantle during subduction, but continental crust does not. And so that has a lot of huge implications for us as well. So there we go. We talked about the crust. Let's talk about the mantle now. He's the big boy of Earth. Very important to understand the mantle. Okay, so the mantle, you probably haven't really thought very much about the mantle, but it is the biggest part of the Earth. And one kind of cool thing, now of course the mantle's very hot. So if you were to look at the mantle, if you were to go down into the Earth and see the mantle, you would just see this glowing bright orange, maybe getting close to white hot, red hot rock, solid rock. Now the reason it's not melting is because it's under a lot of pressure. So that stops the mantle from melting, because by the way, melting temperatures increase with temperature. So if we were going to draw a pressure temperature diagram, so here's pressure on this axis, here's temperature on this axis, and I'm going to draw a line representing the melting temperature of the mantle. It's going to go up. Okay, so the melting temperature of the mantle is going to go up with increased pressure, and of course pressure builds up as you get lower and lower and lower and lower into the Earth, and that's because there's more and more and more rock sitting on top of you. That's why. So the mantle is the biggest part of Earth, both in terms of mass and volume. It's 2/3 of Earth's total mass, and it's composed of stony material that is denser than the crust. Okay. Now, if you were to take the mantle rock and cool it down, what's kind of cool about it is that it would be green. Yep, it'd be green. It's kind of cool, don't you think? It's a green rock. And have any of you ever had a birthstone or a gemstone called peridot? You've ever heard of that? Or maybe you have a piece of peridot. So obviously I can't hear what you're saying, but hopefully some of you have heard of that rock before. So I know this sounds a little crazy, but it's true. The mantle is made of peridot. Peridot is the gemstone name to a common mineral called olivine, which is a green mineral. It's called olivine because it's green like a green olive. Okay, it's kind of an olive green actually. So that's the mantle. It's green. It's kind of cool. So we have, you might be wondering, how do we get a chunk of the mantle like this? And the way that we get chunks of the mantle, we don't drill down. We've never drilled to the mantle. The deepest we've ever drilled is 15 kilometers. So we didn't even get halfway to the mantle. But we've never drilled down to the mantle. The only way we've gotten samples of the mantle is when it's come up during volcanism, because a lot of volcanic liquids start off melting in the mantle. Okay. So the mantle extends down from the bottom of the crust, which is about 30 kilometers down over the continents, 5 kilometers down over the oceans, all the way down to 2,900 kilometers at the core mantle boundary. Temperatures of the mantle range anywhere from 600 degrees Celsius to 4,000 to 5,000 degrees Celsius. Okay. Pressure at the bottom of the mantle is 134 GPa. That is more than 1,000,000 times the pressure at the surface. So it's incredible pressures here at the core mantle boundary. Very, very high pressures. And that's what keeps the rocks from melting, right? So it's high pressures. So like I said, it's very important to realize that the mantle is a solid. It's not a liquid. Okay, there is melting in the mantle, but those melts that are generated usually come to the surface pretty quickly. All right, now I want to talk about this Mohorovicic discontinuity. It's a weird word. It's named after a Czechoslovakian seismologist, scientist during the 20th century. So you do not need to know the word Mohorovicic because everybody has trouble saying it. And so we just call it the Moho. Okay, so the Moho is totally fine for you to just know that term, the Moho. The Moho is simply the compositional boundary layer between the crust and the mantle. Okay, so it is picked up seismologically. So when there's an earthquake, the seismic waves bounce off this layer, and that echo is detected by seismometers on the surface of the Earth. So that's how we know about it. That's how we know how deep the mantle is, because like I said, we have not drilled down into the mantle. So you might ask yourself, how the heck do we know about the depth of the mantle? And we know about it because earthquakes generate these acoustic sound waves, seismic waves. They're mechanical waves. They're shaking the rock. So some of those waves come directly to the seismometer. Some of them go down into the earth and bounce off the Moho, and they are reflected like an echo back to the seismometer, and we can pick up the distances. And that is, by the way, how we know the distance of the core mantle boundary, because some of these waves go into the mantle and they bounce off the core mantle boundary, and they're picked up again as an echo, and that's how we know how deep the mantle, the core mantle boundary is as well, and the inner core, outer core boundary as well. It's all through seismology and seismometers in earthquakes. Okay, so that's how that works. Now, this is one thing very important about the mantle. It's one of the most important facts about this lecture I want you to know. I put this moving lava lamp GIF here to kind of illustrate this. So this is kind of a mind-blowing fact, but it's very true, and it's very important for you to understand. The mantle is solid. It's absolutely solid. Okay, there's nothing liquid about it. However, it slowly shifts and can move over time. so it takes maybe 200 million years. So this little GIF that you're seeing is literally it's simulating the movements, the flow of the mantle. So the mantle can flow, it can move, it actually convects. Okay, so there is convection in the mantle. It's called solid state convection. So it moves, it flows, it convects. However, it mixes. However, it happens very slowly. So this little simulation movie that you're watching here represents, even though it's only 10 seconds long, it represents maybe like 100 million years of history. Okay, so or maybe 70 million years of history. So this process takes a long time. But I want you to realize the mantle is convecting, but it's not a liquid. Okay. The mantle is convecting, but it's not a liquid. So things can convect in a solid form. One thing that you could think of that maybe kind of gives you a little bit more intuition about this is think about metal. Metal can bend and move without breaking, right, and brittly breaking. So when you put the mantle rocks under high enough pressure and temperature, they can kind of bend and flow and move a little bit like a soft metal might be able to do. Okay, so you can almost think of the mantle as like silly putty, even though it's solid rock. Okay, it's not a liquid. So this got a little bit messed up. Sorry for that. I didn't catch this. Yeah, I kind of reformatted all these lecture slides, and I had to go and move everything around, but this got messed up. So we have to talk about this thing called the lithosphere and asthenosphere. So the lithosphere is, I'm going to read this to you because you can't see this exactly. The lithosphere is the part of the solid earth that acts like a stone and breaks brittly. So litho means stone, sphere means a sphere, right? So it's the shell, the hard rock-like brittle shell of the earth. The asthenosphere means stheno means strength. Stheno, like the same root as strength. Okay. Astheno means no strength, and sphere. So this is the no strength sphere. So lithosphere is the part of the earth that can break brittly, like a rock that you're used to, like a cold, brittle cracker rock. It'll crumble and crack. Asthenosphere is the part of the mantle where that is solid rock, but it behaves in a silly putty sort of way. Like it will flow, it will move, it will convect. Okay. So in order to have that convection of the mantle, which was illustrated in the last slide, you have to have this kind of like sufficient pressure and temperature. Okay, so you can't just have cold rock that is moving that way. Okay, so the crust and the topmost part of the mantle are the lithosphere, and the bottommost mantle is the asthenosphere. Okay. So the asthenosphere is part of the solid earth, but it acts very much like stiff, silly putty. It can bend, fold, and deform over time. Okay, so the lithosphere is the crust plus uppermost mantle. It's mechanically strong. It's relatively cool. It's mobile, and plate motions are, so plate tectonics, you've probably heard of plate tectonics. You might know that plates are composed not just of the crust, but of the lithosphere. So when we talk about plate tectonics and plates, we're talking about the lithosphere. So the lithospheric mantle plus the crust, ocean crust and continental crust. So you have to be aware that there's a lithospheric mantle. That's a relatively cooler mantle that is mechanically strong and behaves like a rock. And there's an asthenospheric mantle that is more mobile, can flow, it can bend. And that is the part of the mantle that is on the lowermost part. Okay, so hold on one second here. Sorry about that. My 2-year-old was needing something, so I had to go help her. So anyway, back to the lecture here. So the asthenosphere is the mantle below the lithosphere. It's mechanically weak. It's relatively warm, but not molten. It's very important to realize this is not, we're not talking about molten rocks here. We're talking about solid rocks. And it's a word we can use here is ductile. It means it's deformable. It can easily bend and mold. And this enables the motion of plates during plate tectonics. Okay, so the lithospheric mantle plus continental crust, ocean crust, are going to float along with the convection of the asthenospheric mantle, and that's what drives plate tectonics and plate motions. Okay, so let's move along here. Let me get this out of the way as well. Okay, let's talk about the core. So the core is, like I said, solid iron. Well, actually not solid iron. The outer core is liquid. The inner core is solid, but it is completely metal, an alloy of iron and nickel mostly, but also some other elements that are in there. The core mantle boundary is 2,900 kilometers down to 5,000 kilometers deep, and the inner core is going from 5,000 kilometers deep all the way down to 6,400 kilometers, which is, is the center of the Earth. Okay, temperatures are in excess of like 4,000 degrees Kelvin. You can think of it at this point. You can think of it as 4,000 degrees Celsius. It's white hot. So I mean, if you were down there somehow, you could just take a camera down there and see. It would just be bright, white, glowing hot down there. Okay, so it'd be very bright. You might think of it as being dark in the center of the Earth. You might think like it must be dark, but it's not. It would be white hot, very, very bright to be down there. So you might kind of ask, how do we know about the outer core and the inner core? And one way that we know about it is, that Earth has a magnetic field. Okay, Earth has a magnetic field. That magnetic field is actually generated by the outer core. Okay, and it's generated this way. Have you guys ever? I wonder if I don't do this here. Wait, hold on. Oops, I got out of here. I thought I had a slide about this, but I don't. Have you guys ever done that science experiment in grade school where you took a nail, like an iron nail, that you would put in carpentry to build a house or build something? Okay, so there's your nail, and then you took some copper. Do you guys know what I'm talking about? You take some copper and you wrap the copper, and if you don't believe me, by the way, you can do this. Maybe I should do this in front of you just so you could see. So take some copper and you wrap it around here. Okay, like that. Okay, and you wrap it around the nail. You got to wrap it in a spiral. Okay, and then what you do is you take a battery, right? Okay, so here's your, just, you normal, like maybe like a C battery or a D battery, right? A big battery with some good current in it. And you attach, positive and negative. And what you'll notice is that this nail will become magnetic, and you'll be able to like pick up like a paper clip with it and stuff like that. Okay. So it will have, once you connect the electrical power, it's going to have some, magnetic force. Okay, so what's happening? The current, the electrical charges from the battery are going, and they're spiraling and turning around, going through the copper wire, spiral, turning, and that turning and turning of an electrical charge generates a magnetic field. So basically, you can think of the core of the Earth as a giant one of these. Okay, so the liquid iron core is turning with the rotation of the Earth. It's turning, it's convecting, it's rotating, and those iron atoms carry with it a charge, and that charge is turning and generating this magnetic field. And you know that iron is kind of like a magnetically active metal, right? So it has that extra charge to to actually you'd have to get into all this stuff with electron configurations I don't want to get into, but suffice it to say, I think you all realize that iron, you know how magnets stick to iron, but they don't stick to like aluminum or other things, right? So it's kind of a magnetically active metal, and it has to do with its electrical charge. So anyway, you can think of the outer core as like one of these big electromagnets, and that's what it does. It generates a huge magnetic field. And guess what? Again, you probably never realized this or thought about this, but you wouldn't be alive right now if it wasn't for this. If you didn't have this big churning outer core, which would be a pretty, let's be honest, you probably never thought of the outer core, but you depend upon your outer core. Your life completely depends on it. You could not live on Earth if it wasn't for the outer core. And the reason is that it creates this magnetic field. Well, when cosmic rays from the sun, there are a lot of dangerous, the sun is extremely powerful, right? It generates not just light, it generates UV rays. Or hey, are UV rays good for you? Not really, right? They can really harm. Actually, I think you need UV rays for certain reactions to occur in your body. But for example, it generates vitamin D. But UV rays can also hurt you. It could kill you, right? Too much UV light can give you cancer and kill you. But it's not just UV light. It's X-rays. X-rays are radioactive, right? They're very dangerous, right? There are cosmic rays. There's gamma rays. Very nasty kind of rays come from the sun, but they are deflected or shielded by the magnetic field. So when those nasty solar winds and nasty kind of gamma rays come and strike the magnetic field, it actually generates these beautiful northern lights. So isn't it kind of cool that like these really nasty, horrible cosmic rays from the sun that would destroy our bodies, they would absolutely destroy our bodies, they are deflected by the magnetic field, which shields us from those and creates these beautiful lights. If you go into the northern or deep southern parts of the earth, you get these beautiful lights. So it's kind of cool. I just think that's like something dangerous turns into something beautiful, right? So anyway, how do we know, by the way, that the core is liquid and the outer core is liquid, the inner core is solid, and how do we know how deep it is? Well, like I said, it's all from seismic waves. So you have an earthquake that happens on one part of the earth. You have another seismic station over here. The seismic waves go through the earth. And what's kind of interesting is that there are some kinds of waves called P waves that go through. But there are other kinds of waves called S waves which do not go through, and they bounce off. They bounce off. They cannot be transmitted through a liquid. So that's how we know. It's through analysis of seismic waves that we know that the outer core is a liquid and the inner core is a solid. And it's also how we know how deep something is, because we can pick up these reflections. Let's say there's another seismic station right here. It can pick up these reflections off of the outer core, and we can calculate how deep that outer core is. Okay, so it's all through seismic activity and earthquakes. So again, earthquakes are something that's like they're very destructive and deadly, but at the same time we get all this invaluable information from them. We wouldn't know anything about what is, the composition of the earth and what the earth, how it's structured, if we didn't have earthquakes. So the inner core, I'm just going to end here with the inner core, which is, I don't have too much to say about it. There's not too much to say, really. The inner core is solid. We know that through seismic analysis of seismic waves. It has some lighter elements in it. And it extends from the base of the outer core, 5,000 kilometers, down to the center of the Earth, 6,400 kilometers. And it's made of that right iron nickel alloy. So that's all you have to know. I hope you enjoyed the lecture. I hope you kind of found something out today you thought I think is interesting. And I'm going to end right here, and I hope you enjoyed it, and I'll talk to you again next week. So have a good week.